Good morning, everybody, and welcome to lesson 7.2. Today, we're going to talk about how we can use differential equations to write things about exponential growth and decay. So let's get cooking, looking at exponential growth and decay. So this is an example of a problem that you would have seen in Algebra 1. Hopefully, you remember this formula, P times E to the RT from Algebra 1. And what we're going to do is we're going to use calculus to show why this formula works. So we can think about it like this. This is an interest problem that's talking about how much money will be in the account out for a certain amount of time, and it gives us an interest rate of 4.5%. So what that 4.5% helps us do is it helps us say, well, the money in the account, the rate at which the money in the account changes is directly proportional to the amount of money in the account. Because if I have more money, my money grows faster using this rate 0.4 or 4.5%. So what I can do is I can say, well, if A is the amount in the account, I can say dA over dt, so the rate of change in the money over time is equal to K, which is a constant proportionality times A. So what this means is there's some kind of direct proportionality here between the amount of money, between the amount of money in the account and the rate at which the money in the account grows. So now I'm left with this that I can solve using separation of variables. And in this case, because my rate was 4.5%, I know that my K is going to be 0.045. So I'm going to use that in a minute to set this up. So basically the idea here is the rate at which the amount changes is directly proportional to the amount of money in the account. And now this is something that I can solve using separation of variables. So we saw separation of variables last time. So I can say dA over A equals K dt, integrate both sides of the equation. L of the absolute value of A is equal to KT plus C. And we're going to assume here that the amount of money in the account is positive. So there's an actual value for this. So what we're going to do now is we're going to exponentiate both sides of the equation. And I'm left with A is equal to E to the KT plus C. So I'm looking at this and I'm saying, well, I mean, this isn't exactly what I had before. But if I think about it like this, E to the KT plus C, I'm going to remember my exponent rules. I can rewrite E to the KT plus C as E to the KT times E to the C. And I notice that this part right here, this is just a constant. So E to the C is still some kind of constant. So I can write this amount as C times E to the KT. And now this looks a lot like my PERT formula, P times E to the RT. So in this case, and really in most cases when we end up with something like this C is going to be my initial amount, just like it is in the PERT formula. So that's the initial amount. And that would actually be pretty easy to figure out because if I ever plug in 0 for t, I'm left with just c is equal to a. And then right here, so in the case of this problem, k was our rate. All right, so this is the general idea for how to set up and solve a differential equation to talk about exponential growth and decay. One other thing that I want to note is we made this positive k because we know that the amount of money in the account is growing. If this had been exponential decay, so the amount of money or something else, like maybe the price of a car decreasing, this would have been negative k because the derivative would then be negative. So that is it for today. That is the general idea. Again, this is not meant to be all encompassing. We will go over this more in depth in class, but today we kind of briefly talked about exponential growth, exponential decay, and then how we use separation of variables to create a model for exponential growth and decay. So I hope you took some good notes. If you have any questions, bring them to class. And I hope you have a fantastic day. I'll see you in the next video.